Hi, everyone. This is James Baumhoff. I'm the organizer of the webinar today. And so it's 11:55. Just to let you know, we will get started in about 5 minutes. We'll just wait for more people to join. Okay, I think we'll get started. Well, welcome everyone to a CSHS webinar. Thanks for signing up and thanks for joining us. My name is James Baumhoff. I'm the current president of the CSHS, and I'll be today's webinar host. So today's webinar is, as you all know, on the fundamentals of flood frequency analysis, as presented by Chris Doherty and Dr. John Perdicaris. So Chris and John, they're working to educate practitioners on flood frequency analysis, and they came to CSHS for help with promotion of the material that they've created and the program they've created. And so a webinar on this seemed to be a perfect fit. And we've had over 200 people sign up for this webinar, so it seems like it's a very relevant topic for Canadian hydrology. So um, looking forward to it. So I'll just give a brief overview of the structure of the webinar. First, I'd like to give an intro to CSHS because a lot of people on this call likely may not know what it is. Then we will go into the actual presentation. The presentation is about 35 minutes, and the authors have requested that it be a pre-recorded presentation so that all the material was ensured to get in. So if you do have a question during the presentation, please just type it in the box on the right-hand side of your screen, I believe, and I'll receive all those questions. And then at the end, we'll ask those questions to the panelists. So Chris and John, of course, are on the line, and we'll be happy to answer any questions you have after the presentation, and that'll happen during question period. So just a few housekeeping things. For audio, this is actually the first time I'm using this presentation software. It seems to work fairly well. There's two ways to connect for sound, so hopefully you can all hear me by now. You can connect via your computer, or you can call in via your phone. So if you are having audio issues, just try using the method that you haven't already tried. And just to let you know, the webinar is being recorded, and a link will be sent out afterwards. I'll send out an email to the email you provided when you signed up to this webinar. And if you do have a question during question period, you can unmute yourself, or you can put your hand up. There should be a little hand icon, and I can unmute you as well. So we'll see how that goes. We have the webinar booked for an hour, so we should be finished around 1 o'clock Eastern. Okay. So CSHS is the Canadian Society for Hydrological Sciences, and their mission is to promote the science of hydrology and its sound application of effective water management. So it's a affiliate organization of the Canadian Water Resources Association, and it's existed since 1992, I believe. So some of the ways that we promote or fulfill this mission is through courses that we co-sponsor. So one of the courses is a hydrology course in Kananaskis country, and that's been running since 2010 with the University of Saskatchewan. And that's a 10-day course at a field station there. The picture you see is one of a class from a few years ago at a weather station in the area. And then there's a second course on hydrological modeling, which is a 5-day course and put on at the University of Waterloo, and that typically happens in June and has been running for 4 years. One of the other things we do is develop and promote modeling tools for the hydrological community. So if you go to greyjproject.org, the website's on the bottom. It will give an overview of the modeling tools we've helped create. Of one in particular is the Hydrology R package. So R is a free source and open coding language, and there's a group that has developed tools for Canadian hydrologists to help them do their jobs. The other thing we do is webinars like these, and then we also help out with the CWA conference. So that's a little bit about CSHS. If you'd like to get involved, I'll have an email at the end of the presentation, or you can just go to greyjproject.org. So without further ado, we will get to the presentation. I will just load it up here. So again, the presentation's about 35 minutes long, and we'll have questions after the presentation.
Welcome to Fundamentals of Flood Frequency Analysis. Today our presenters are Chris Doherty, Director of Environmental Water Resources Group Limited, and John Purdy-Karras, Senior Hydrotechnical Engineer, Ontario Power Generation, and Adjunct Professor in the Department of Civil Engineering at Ryerson University. Chris Doherty is the Director of Environmental Water Resources Group Limited. Chris has over 40 years of consulting experience and is the co-author of several guideline documents. John Purdy-Karras is a Senior Hydrotechnical Engineer at Ontario Power Generation. He is also an Adjunct Professor in the Department of Civil Engineering at Ryerson University. John has over 20 years of engineering experience and is the author of several publications.
The first thing I'd like to discuss is where does flood frequency analysis fit into the overall process of generating return period flow rates and the accuracy or the hierarchy of the different methods. Generally, flood frequency analysis is the most accurate method of determining flow rates. It's followed by regional frequency analysis, then by continuous simulation modeling, and single event modeling. This is generally. There are instances where flood frequency analysis may not be more accurate than the other methods, such as where the land use is changing in the upstream watershed over time. It's the same thing with continuous simulation modeling and single event modeling, where depending upon the time step and the percent imperviousness, single event modeling could be more accurate than continuous simulation modeling. But in general, flood frequency analysis is the most accurate method of generating flow rates, and so it becomes critically important to a hydrologist and has to be one of the things in their toolbox. The objectives of flood frequency analysis is to determine, one, the return periods of the observed streamflow data, two, select a frequency distribution that best fits the observed streamflow data, and three, to determine streamflow rates for return periods beyond the range of observed data using the frequency distribution. This was roughly the process or the objectives outlined by Jeffrey Kite in his 1976 document, Frequency and Risk Analysis in Hydrology. A couple things that I wanted to point out at this point. I see a lot of studies that basically use the selected frequency distribution to determine all of the return period flow rates. I'm not a real fan of this. If we have observed data, I think it's more important to get the return periods of the observed data and use those rather than using the frequency distribution. The second thing I'd like to point out is that Water Survey of Canada really does not measure streamflow rates, rather it calculates streamflow rates by measuring stage and streamflow velocity and the flow area dimensions of the watercourse. In our presentation, we have substituted observed instead of recorded streamflow. Calculation of the streamflow rates introduces error and uncertainty into the observed streamflow rates. The accuracy of streamflow rates is dependent on a number of items, and the accuracy becomes important because I've seen a lot of instances where people try and improve the level of their accuracy of their solution past the point of the actual input data or the streamflow rates in which they're trying to compare it to. The accuracy of streamflow rates is dependent upon the accuracy and precision of equipment, and you can see this when you're using an apple, say for instance, you throw it into the stream in order to try and get an estimate of the streamflow velocity. Better methods to use in order to get that velocity. There's also the methods used to develop rating curves and average depth methods. I've seen some people interpolate rating curves using a normal approximation, while others have a tendency to use a log-log curve in order to fit streamflow points. There's the skill of the hydrographer, and whether you're experienced or inexperienced, it has a lot to do with the answers that you come out, especially when you start estimating answers, for instance, under ice flow conditions. There's also channel stability, where if the channel is eroding, then trying to get stage measurements that you're going to relate back to the rating curves can make a difference in the accuracy of the answer that comes out. And also the climatic and environmental factors. And so when you're out there trying to take streamflow measurements and you're in the middle of a snowstorm, one has to question the accuracy of the results that you're getting. So the next question is really to sit down and try and look to say, okay, what is the accuracy of the stream flow measurement? Hydrology of Floods in Canada by Watt and et al. Describes errors in annual maximum discharges of someplace in the neighborhood of 10 to 15%. When we come to looking at something like the flood of record, Watt is saying the accuracy could be up to 50 or 100%. So when we start doing frequency analysis and we're really trying to get an answer that's closer than 10 to 15%, one has to really question the results of the distributions that we're using, especially at the 10% level when we're looking at this. Um, Another source of looking at accuracy of streamflow rates is the United States Geological Services, who does a lot of the measurements of streamflow within the United States. They basically said that for 95% of the time, if the streamflow rates are within 5%, that's excellent. Good is 10% level, fair is 15% level, and poor is greater than 15%. And they're looking at roughly the same for individual storm events, that 15% is the level of accuracy that you get. If you compare the USGS with Watt, you know, getting answers better than 10 for 15% is probably, exceptional if you can get them better than that. So when we start pushing our distributions, if your answers are within 10 or 15%, then you've probably gone far enough in your efforts. When we look at this, the same thing can be said that if you're using computer simulation models and you're trying to calibrate and validate the models, and if you're coming within 10 or 15%, you're probably doing an adequate job. I think the next consideration we should look at before we get into doing the flood frequency analysis is really how far do you stretch the analysis. A general rule that I've always grown up with is 2 times the length of the observed streamflow data. So if you have 30 years of data, you probably shouldn't be pushing it past 50 or 60 year return period. A lot of the studies I see today, they take it out to 100, 350, or even out to 1,000 and 1,500 years. Watt has a similar rule of thumb, is about twice the length of observed streamflow data, probably because we're of the same age group. But if you come back and you start looking at risk analysis and you say, well, okay, what are the chances that my 2-year return period has occurred within a 30-year period? That's about 100%. Same with a 5-year. You're pretty much guaranteed that you've seen a 5-year flood within 30 years of record. When we start getting out to 10 years, it drops to about 96%. And as you can see, at 25 years, we're down to 70%. At 50-year mark, you're down to 45%. And at 100 years, you're down to 26%. If you carry it a little farther, when you get out to 350 years, it's 8%. And 1,000 years, it drops to 3%. So when we start looking at the results from the flood frequency analysis, your level of confidence in the numbers as the return period starts to increase should be reduced. Given that we don't have a lot of stations within Canada at the 50 or 100 year level, we're really pushing our data when we start looking at return periods of 50 and 100 years, let alone 350.
There are many mathematical measures that can objectively summarize the nature of a dataset. This variety is required for several important reasons, including 1. To help identify an appropriate frequency distribution to characterize the dataset, and 2. To characterize this data in a manner that allows comparisons between datasets. We are going to look at several different measures to characterize the data, the first being the mean. The arithmetic mean is the first moment about the origin, sometimes referred to as the center of gravity, of the data set. This example here shows the mean about a normal distribution. The next moment we will discuss is the standard deviation. The standard deviation is the second moment of measurement to describe the data. The standard deviation is a measure of the dispersion or the spread of the data around the mean. The current graph here shows a description of the standard deviation as it moves away from the mean.
The fourth moment about the mean is the kurtosis. The coefficient of kurtosis is a measure of the peakiness of the distribution. In flood frequency analysis, a graphical study of the characteristics of the data sample must be undertaken. Graphical data descriptors illustrate the character of the data set. This example here illustrates the relationship between streamflow and rank. A histogram is a plot that indicates the frequency at which data occur within discrete intervals, specifically the relative number of occurrences of an event within the class interval or concentration. The frequency distribution is often represented in the form of a histogram, the principle of which is based on the fact that the area of each rectangle represents the proportion of observations falling in that interval. This example here illustrates a histogram of streamflow discharge. In this example, we see a histogram of discharge by month. According to the graph, the majority of high flow events occur during the month of April, indicating that most high flow events occur during the spring freshet. In addition, there are certain advantages of using histograms as a means of visual representation of the data. Number one, the total range of the data in a sample is readily apparent. Number two, the most frequently occurring value can easily be recognized. Number three, the range of greatest abundance can be readily identified. And finally, the general shape or character of the distribution of the data becomes easily discerned. In this example here, we see a time series plot of maximum instantaneous flows. Time series plot offers certain advantages as a means of visual representation. First, any trends to the data can easily be detected. And second, any high or low outliers within the data sample set can easily be identified. In order for the results of a flood frequency analysis to be valid, the data series must meet certain statistical criteria. These criteria include, number one, that the streamflow data must be from random events. These events must be independent. There can't be any trends to the data. And the data sample has to be from a single population or homogeneous. In a hydrologic context, randomness means essentially that fluctuations of the variable arise from natural causes. Flood flows appreciably altered by reservoir operations cannot be considered random unless the series is first deregulated. Published flow records, however, may be termed regulated, although the regulation is not really significant. The term natural flow, on the other hand, always means that the flow is not regulated and may generally be regarded as random. There are currently no suitable tests for hydrologic series that are currently available. However, in CFA 88 or CFA 3.1, the total number of runs above and below the median of the sample data are used as a measure of the randomness of the data sample. Even if events in a series are random, they may not be independent. Large natural storages, for example, may cause high flows to follow high flows and low flows to follow low flows. The dependence varies with intervals between successive elements of the series. Dependence among successive daily flow values tend to be strong, while dependence between annual maximum values is generally weak. In some cases, however, There may be significant dependence even between annual maximum values, for example, in the case of very large storages, such as the Great Lakes. There are several tests that are used to test the independence of the sample data, including Anderson, 1941 as described in Chow, 1964, Wald and Wolfowitz, 1943 test as described and applied in Bowlby and Robitaille, 1977, and the Spearmint rank order serial correlation coefficient as described in NERC, 1975. Stationarity means that, excluding random fluctuations, the data series is invariant with respect to time. Types of non-stationarity include trends, jumps, and cycles. Jumps are normally due to an abrupt change in a basin or river system, such as the construction of a dam. Trends may be due to gradual changes in land use. Cycles are often associated with long-term climatic fluctuations. There are currently several tests that are used to determine if there is stationarity within the data sample set. These include the Spearman rank order correlation coefficient test for trend, as described in NERC 1975, the Mann-Whitney test for jump by Mann and Whitney 1947, and the Wald-Wolfowitz test for jump by Siegel 1956. Homogeneity implies that all the elements of the data series originate from a single population. A series that contains both snowmelt and rainfall floods may not be homogeneous. However, depending on the results of a test, it may be acceptable to treat it as such. There are two tests that are commonly used to determine if a data set is homogeneous. The first one is the Mann-Whitney test, Mann and Whitney, 1947, and the second one is the Terry test, 1952. A number of probability distributions used for hydrologic frequency analysis in Canada are listed here. The Entrance-Fram normal, or Gaussian distribution, is symmetrical about the mean. Has not been used exclusively in flood frequency analysis because most flood series have a pronounced positive skew. However, it has been found appropriate for certain series of flood discharges and water levels, particularly where there are large storages. The log normal distribution was first applied to flood series by Hazen in 1914. It implies a normal distribution or the log transformed variate. Chow, 1954, presents a theoretical justification of its use for hydrologic events, which are the result of the joint multiplicative action of a large number of independent causative factors. It has been used extensively for flood flows in Canada and the United States because of its robustness and ease of application and interpretation. It should normally be considered as a prime candidate for flood discharge series. The three-parameter log normal, this variant of the log normal distribution, can be used where the log transform variate is significantly skewed. Its application to Canadian flood data was first reported by Sangel and Biswas in 1970. Extreme value type 1. The extreme value type 1 distribution, otherwise known as the Gumbel or double exponential, has been applied extensively both to floods and storm rainfall and is generally employed by Meteorological Services Canada for analysis of short duration rainfalls. A variant using log transformed data, referred to as log Gumbel, was formerly used in Canadian flood studies, but is now no longer in general use. The extreme value type 2, or Fréchette, references for early applications are given by Gumbel 1958. One of these was for wind speed, Thor 1954. A comprehensive analysis of floods in the United Kingdom found that for most regions the type 2 distribution was the most appropriate. The log Gumbel distribution referred to above is a special case of the extreme value type 2 distribution. The extreme value type 3 is the third case of the general extreme value distribution. Outside of the United Kingdom flood studies, it has been applied very infrequently. Pearson type 3. This distribution, one of a series derived by Pearson, has been used for flood analysis in parts of Canada, particularly in Alberta. It is more commonly used with the logarithmic transformation, which is often referred to as log Pearson type 3 distribution. This distribution has been used extensively for flood frequency analysis in the United States, following a recommendation by the U.S. Water Resources Council in 1967. A publication, U.S. Interagency Advisory Committee on Water Data from 1982, provides a complete guide for users. An event, Qt, corresponding to a return period t, or exceedance probability 1 over t, can be expressed for any distribution in terms of a general relationship proposed by Chow. Qt is equal to x bar plus kt times s. where x bar and s are the population mean and standard deviation respectively, and kt is a frequency factor which depends on the distribution, the return period t, and the coefficient of skewness in the case of three-parameter distributions. In the case of estimation by the method of moments, x bar and s are estimated by the mean and standard deviation of the observed streamflow values. When selecting a distribution, people will often select a distribution that best fits the data, usually through graphical representation. However, there are many distributions with an acceptable fit to the sample data set. In some cases, none of the distributions may fit the data well, in which case the user must then resort to another type of analysis, such as a regional frequency analysis. The selection of the best fit distribution is often subjective, and there's no procedure to select the best fit. Most likely, no one distribution will be acceptable to all users. One can use the following 4 steps as a guide for selecting a distribution. First, review the upper and lower distribution bounds. If the distribution has an upper bound, this could underestimate your flood flows. However, if the upper bound is high enough, this will have little consequence on your results. Second, compare the streamflow statistics with the theoretical values, specifically the coefficient of skew and the coefficient of kurtosis. Third, undertake a visual assessment of the fit, particularly the return period streamflow rates with the distribution curve. And finally, undertake statistical goodness of fit tests, including the chi-square test, Kolmogorov-Smirnov test, the standard error, and also the Anderson-Darling test. The standard error is expressed in terms of the sample standard deviation S, the sample size N, and a factor gamma t. Now gamma t is dependent on 2 parameters, including the return period and also the probability distribution. Expressions for gamma t for different distributions were published by Kite. With respect to the standard error, it essentially quantifies the level of reliability within the frequency analysis. However, if one wanted to express that frequency analysis as a graphical plot, or that reliability as a graphical plot, then they would be looking at establishing both upper and lower bounds. When undertaking a flood frequency analysis, a question that is often asked is just how reliable are our flood flow estimates or forecasted flow estimates of our QT values or flow values. One approach is to plot up a series of curves for every return period flow rate above and below the frequency curve. For example, if we were to take 2 times the standard error and for each return period, and we were to plot it against the frequency curve, we'd essentially establish an upper and a lower bound of our frequency curve. If our curve was a normal distribution, then this would be equivalent to the 95% upper and lower confidence limits. Having said that, essentially the confidence limits are a function of the standard error at a specified distance. When looking at standard error, as I mentioned before, your standard error is essentially a function of your probability distribution or frequency distribution, and also your return period. As a result, your confidence limits are also a function of that frequency distribution and your return period. So the confidence limits are specific to each return period. An alternate to establishing confidence limits, or what is often also referred to as reliability limits, is a series of error limits. The error limits are essentially a function of the return period and the years of record. So your error limits, if you had 30 years of record, would be significantly different than if you had only 10 years of record or if you had 100 years of record. Weisman actually published a number of error limits as functions of return periods and years of record. As I mentioned earlier, 2 statistical goodness of fit tests that can be used to test how well your sample data fits a given frequency distribution is the chi-square test and the Kolmogorov-Smirnov test. Now, in the chi-square test, essentially what you're trying to do is determine how much of a significant difference there is between your expected and observed frequency. So really you're looking at testing a null hypothesis. In the Kolmogorov-Smirnov test, the Kolmogorov-Smirnov statistic essentially quantifies a distance between the empirical distribution function of the sample and the cumulative distribution function of a specific frequency distribution, or what your reference distribution is. So if you're using multiple distributions and you want to determine how best that data fits your given frequency distribution or a given frequency distribution, you can use either the chi-square test or the Kolmogorov-Smirnov test as a way to determine how well your sample data fits the a specific frequency distribution. Again, there are other tests that can be used, not just these two. However, both the Kolmogorov-Smirnov test and the chi-square test have been used quite a bit in flood frequency studies. They've also been used in other probability studies also. When undertaking a visual assessment of the fit, one can plot and compare several different probability density functions with the histogram of the discharge. In the current example, we see a comparison between the log Pearson type 3, the log normal, the gamma, and the normal distributions. In this table, we see a comparison of the theoretical coefficient of skew with the actual coefficient of skew for different frequency distributions. In addition, we also compare the theoretical coefficient of kurtosis with the actual coefficient of kurtosis for the same distributions. In this example, we see the sample data plotted with the normal distribution curve. In addition, the upper and lower 95% confidence limits for the normal distribution have also been plotted. The following table lists the results of the goodness of fit tests for the different frequency distributions. The goodness of fit tests include the coefficient of determination, the Kolmogorov-Smirnov test, and the chi-square test. In the case of the coefficient of determination, the greatest value is the best fit. For the Kolmogorov-Smirnov test and the chi-square test, the least value is the best fit. The following table lists the return period flow rates for the different frequency distributions. The log Pearson type 3, 5-parameter Wakeby, and generalized parameter distributions were determined to be upper bounded. The 2-parameter log normal, 3-parameter log normal, exponential, and Gobel distributions provided a poor visual fit, and the normal, 2-parameter gamma, Pearson type 3, Weibull, and logistic distributions provided a good visual fit. The following table compares the observed streamflow rate with the forecasted streamflow rate for different return periods. The forecasted streamflow rates were determined using a Weibull distribution. When comparing the observed streamflow rate with the forecasted streamflow rates, the percent difference in peaks is less than 5%. For example, for the 2-year event, the observed streamflow rate was 80 cubic meters per second, and the forecasted streamflow rate was determined to be 86 cubic meters per second. For the 5-year return period, the observed streamflow rate was 123 cubic meters per second, and the forecasted streamflow rate was 117 cubic meters per second. Similarly, for the 25-year event, the observed streamflow rate was 142 cubic meters per second, and the forecasted streamflow rate was 151 cubic meters per second.
We've put together a flood frequency analysis course, and I guess the reason why the course, originally we started out as a flood frequency analysis project for one of the conservation authorities. We were using Environment Canada's CFA program, or Consolidated Frequency Analysis. The program has 4 distributions, and what we found that the distributions weren't sufficient. None of the data seemed to be fitting any of these 4 distributions well, so we decided to look at other distributions. During the literature review that we went through, some of the presentations seemed to be overly complicated for what we were doing. So we identified that there is a need to simplify flood frequency analysis. Also, at the same time, we found very few worked examples. And since we had to go through and work out the examples for the project, we thought this would be a nice, the work that we had done would probably go into a nice 1 or 2 day course. Our course that we're putting on basically includes a computer program that's intended to do all the calculations the hand calculations that we show you how to do in the course. The reason we're not looking at CFA or the Consolidated Frequency Analysis program is for a number of reasons. One, it was last updated in 1993. The program originally got its start by Jeffrey Kite, and then it got turned into the program called FDRFA, Flood Damage Reduction Analysis, Flood Frequency, by Condi, Boone, and Nix. This was during the 70s and 80s. Paul Plion and Harvey basically transformed the flood damage reduction program into CFA version 1 by looking at some of the work that was done in the NERC program in England. The program was last updated in 1993, as I said. Nothing seems to have been done since then, and Environment Canada really doesn't seem to want to modernize the program. The program was compiled for older PCs. It was written in Fortran 77, but since then, since 93, we've had quite a push on computers, and 8-bit programs that were compiled have to run on a DOS emulator at the moment. The interface is slow, it's actually annoying, and we found there is little to no control on formatting of the output. During the course, we will show the attendees how to do basically all of the work by hand, with hand calculations or a spreadsheet program, whichever is easiest for the attendees. We show you how to do the calculations for the 4 tests of randomness, trend, homogeneity, and independence. Also, the outlier test by Grubbs and Beck. We'll show you how to do the 11 distributions through the method of moments, and the confidence limits, which are not in CFA, but most guideline documents request that you do. We'll also, as part of the course, give you templates for Microsoft Excel, which will allow you to plot the output from the computer program. It's the same graphs as in CFA, and we'll also show you how to do the flood frequency plots on a Microsoft Excel. The course also includes a computer program that we've put together to conduct the same calculations that we show you how to do by hand. That's the statistical tests and the return period flow rates, frequency analysis, and also separates out the data so that we've got input for the Microsoft Excel graphs. The program runs on Mac OS X and Windows 7 at the moment. Hopefully get it into Linux in the future. It's written in Fortran 95. The input is through Microsoft Excel. You put the data in using a spreadsheet. You save it as a CSV file. The program takes that, runs it through, and the output is also in CSV files, which you can then import into Microsoft Excel. We have the XY values for the graphs and tables, and we give you the templates to do it in Excel. We're currently looking to see how much interest there is in a flood frequency analysis course. We're looking at about 15 hours of instruction. A computer program accompanies the course, and the delivery will be voice over whiteboard. Approximate cost is about $1,500 per person. Now the delivery, it's open. We can do this a number of ways. So if you have any interest, please get back to us, ewrg@idirect.com, and we'll see what we can put together. Also, at the same time, if you have any comments on what you'd like to see the program do or what you'd like to see in the course, please get in touch with us. We thank you for today, and we're here to answer any questions you might have.
Okay, thanks a lot, Chris and John. Chris, make sure that your mic is on. Okay, Chris, is your mic on? Can you talk?
Yes, we're here.
Okay, great. John, I know you had some issues with your phone. Are you there?
Yes, I am.
Okay, great. There were a couple messages. Some people were having issues if they were on the phone listening to the presentation. I apologize for that. I'm not sure why that is. For most people, it seemed to work. Just know that everybody will receive an email with the presentation, with obviously the full audio of the presentation and this question period. That email will be going out tomorrow. So if you missed it when it was live, you'll be able to see it in a bit. So we do have a few questions. The first one was just a comment. It says, unfortunate use of accuracy in the early slides should be uncertainty. Chris or John, do you have any comments about that or know what that's reference to?
Can you repeat that question again? Because I don't really understand what the person is asking.
Yeah, I guess they're asking you to discuss the difference between accuracy and uncertainty. It seems, I guess, beyond that, I'm not sure. Robert asked the question. If he's online, he could feel free to unmute yourself and elaborate.
If I could for a second, I would probably agree. You know, the term uncertainty might be a better word to use in place of accuracy, and we can make that change in the future.
Okay. The next question is, it says, about distribution, Western and Eastern Canada should be different. Even in Western Canada, Alberta and Saskatchewan might not be the same, all because the hydrological processes, topography, and changes are not the same. Is this correct?
Yeah, that is actually correct. In fact, here in Ontario, back in the 80s, we had initiated a number of studies as part of the Canada-wide or Canada-Ontario-wide flood damage reduction program. And it was a joint effort between the NRC and Environment Canada, particularly Water Survey, to look at all the gauging stations that were currently here in Ontario. And they did look at flood frequency analysis for all the stations. And I think there was a report that was published around the mid 80s, and they had recommended for Ontario at least that the two distributions that are probably the most representative of the data at that time. If you had a positive skew, they recommended that you use the 3-parameter log normal distribution, and if you had a negative skew, they recommended that you use the log Pearson type 3 distribution. That is not the case throughout Canada. Every basin or every watershed is unique. It has its own characteristics. So when you go about selecting the distribution, as what Chris had mentioned, what I had mentioned, we sort of set up a guideline of things that you can use to see which distribution best fits your sample data. Because they are quite right. I mean, you do have differences in climatic conditions, you do have differences in hydrologic processes, and therefore those are going to tend to influence your results. So just because there's a certain distribution that was recommended at one point in time for Ontario, that's not going to be applicable throughout Canada.
Oh, okay, thank you. That makes sense. The next question is from Henry Vieira. It says I may be getting this pronunciation wrong. The Kolmogorov test usually looks at whether a threshold is surpassed or not to determine whether a distribution is suitable to the degree of confidence we are interested in. However, if I'm interested in comparing which two distributions best represent the data and both satisfy the KS condition, say log normal versus Gumbel, can we simply consider that the distribution which has the smallest difference can we sorry, can we simply consider that the distribution which has the smallest difference is the best one? I'll try to go ahead.
I was going to say is that when we looked at the group of distributions that we had, there may not be any one distribution which fits the data well, even though the statistical test would seem to indicate that. And what we found in the example that John showed was that 4 of the distributions or 5 of the distributions didn't fit it very well at all. Some were upper bounded, and we ended up with 4 or 5 distributions that seemed to fit the data okay. So I think when you get down to the tests, all of this starts to become kind of a subjective. Every user is, or modeler is going to come up with a different distribution. And the idea is that when we started looking at the selection, we really wanted to look at the entire picture, the whole group, and then we end up using engineering judgment to pick one out.
Yeah.
John, you have anything to add?
No, just with regards to goodness of fit tests, there's other tests that you could run that you can do also. People have used correlations where they compare the empirical frequency values with the actual distribution frequency values. People have also used the Anderson-Darling test as a statistical goodness of fit test. I guess there is no procedure as to which test to use or what test to use in what order and which test you should be giving priority to. Most of the literature that I've looked at always recommends not to, I guess, put all your eggs in one basket, not depend just on one single test, but to do multiple tests. And as Chris was saying, when you do that, sometimes, yes, you might score well one distribution over the others using the Kolmogorov-Smirnov test, but then that same distribution won't do as well using the chi-square test. So usually you want to use a combination of different goodness of fit tests or statistical goodness of fit tests. But before you even do that, you want to also look at your data and just plot it and see how well it fits the line. You know, you want to do now the first visual assessment of the fit, and or as Chris was saying, you know, do a graphical plot, see how well your data fits the actual probability or frequency distribution. And that's usually the first check that most people do, is that visual inspection. The other thing you could do is, as we mentioned, is you can compare the theoretical and actual values of the third and fourth moment, or this coefficient of skew and the coefficient of kurtosis. Ramad and Rowan Hamid published a book in '99 on flood frequency analysis, and in it they presented a series of polynomials which compared, which built relationships between skew and kurtosis. So you can actually take those polynomials and you can use them to see how well your actual sample skew and kurtosis match the theoretical values. And that could be another test also. So I guess the point is, don't just depend on one single goodness of fit test or one single method of checking to see how well your data fits your distribution. You want to use a combination of all of them. And then you just want to rank them accordingly when you do that. And you probably want to give somewhat of an equal weighting to each methodology that you're using to check your data against the frequency distributions.
Okay, thank you. We've got lots of questions, so I'll try to get through as many as possible. Next one, is the software available for sale without taking a course?
No. Well, I'm a very firm believer is that you should know what the program is doing. And the easiest way, we started out with this, is user manual, but obviously the user manual just drops down into a course.
Okay, so I would, I guess, point this user to your email address and contact you through there, which I will put up right now, actually.
Thank you.
So their email address is ewrg@idirect.com. The next question is, any recommendations for flood analysis of ungauged areas?
Oh, that's a good one, actually.
Could I just hear the question again? Are we going
Yeah,
back to that table of hierarchy of methods?
No, actually, the question, Chris, was, is there any recommendations for catchments or basins that are ungauged?
A regional
If you have an,
frequency analysis.
yeah, I was going to say that usually, as Chris was saying in his, I believe it was his his first slide, and this actually was published in the 1987 floodplain management guidelines or technical guidelines for Ontario. There's a bit of a hierarchy. If you have a gauge at a catchment or basin outlet, usually you're to use to do your single station flood frequency analysis. If you don't have a gauge and you have an ungauged catchment or basin, then the recommendation is to use a regional flood frequency analysis if a regional flood frequency analysis is available. So you'd have to see where your basin is, and I guess you have to look at the surrounding watersheds or basins and see what surrounding gauge stations there are. When we did our regional flood frequency analysis back in the mid-'80s, or when Ontario did them as part of the Canada-Ontario-wide flood damage reduction program, they actually broke up the province in a series of regions. Now, those regions were based on secondary watershed boundaries. Now, that's not the only way you can break up the province. You can also break it up into ecozones, which we have done. So you can break up, if you have ecozones for your province or respective province, you can group all the gauges or watershed candidate gauges within that each ecozone, and you can go through the process of doing a regional flood frequency analysis for that gauge. So if you don't have a gauge catchment or basin, then yeah, a regional flood frequency analysis would be your next option. After that, there's computer modeling, whether it's continuous simulation or event simulation. So that's another option too. Hope that answers the question.
it did for me. So the next two questions are about climate change. I'll actually read them both together because they are so related. It says, during the course, are you going to include FFA under climate change? I mean, to take into account non-stationarity. So that was the first question. And then the next one was, how do you recommend dealing with climate change and estimating future peak flows under climate instationarity?
Okay. Do second question first because it was easiest. Lately, we've just finished a technical guideline document for flood hazard mapping for the Toronto and Region Conservation Authority. In it, we took an adaptive approach where we use a sliding 50-year period to do the flood frequency analysis and also precipitation analysis. I think we came up with a lot of questions when we were writing the document that what do we use as a climate change value, whether we're tacking on 10%, 5%, etc. It was also brought up that we don't know if even climate change is going to occur in the watershed that you're in. So we felt that kind of an adaptive process would give us better results.
Yeah, actually, just to add to that, and this will hopefully answer also the first question about climate change and how do you account for it in flood frequency analysis. I've been recently involved in a research project where we actually looked at a series of, as Chris was saying, of 20-year periods of future climate over the next 100 years. What we've done essentially is we've taken each of those 20 years and we've taken all of the different ensembles of climate change models. So we have a meteorological time series for those 20 different periods, and then we basically then run them through a lumped hydrologic model to come up with some continuous flows for each period, and then we actually do the flood frequency analysis for each period. So one approach would be to basically do some climate modeling and come up with a meteorological time series over the next, say, 100 years. And you can break it up into 30-year or 40-year periods, and you can use a sliding average or average period. And then from there, you can run them through a lumped hydrologic model, or it doesn't have to be lumped. It could be discretized or detailed hydrologic model, and basically come up with a continuous time series for the same period, and then conduct your flood frequency analysis on those simulated flows.
Okay, thank you. We're getting a lot of questions, and unfortunately, we just have time for a few more, so we won't be able to get to all of them. So my apologies if you've sent in a question and I haven't got to them. The next question is, I heard peak FQ from the EPA, which is the Environmental Protection Agency in the United States, can do flood frequency analysis. Is it available for Canada too? What is your comment on that?
I don't think it's available for Canada, but it is available for the States.
Okay, so that's...
I believe it's using the USGS streamflow data for that analysis.
Okay. The next question, the annual maximum flow rates on the Bow River in Alberta over the last 140 years shows about 10 very high rates, mostly before 1932, and many low rates with the exception of 2013. Would it be reasonable to treat these data as one continuous series to generate return period flow rates? It seems this has often been done in flood frequency analysis for the city of Calgary over the last 50 years.
I guess it depends what your objective is. If your objective is really just to determine what is the highest or what is the greatest flow or what is the highest the water level is going to get, then yeah, you can use all the high values, and but you can also do a high and low outlier test on the data too, and you can eliminate any high or low outliers within the data set. But if your objective is really just to determine what is the highest the water is going to get or what is the highest flow, then you probably do want to incorporate the continuous time series in your analysis.
And if I could just add a point here, if I'm not mistaken, the Bow is glacier fed. And if climate change is occurring, you may find that you've got as the glaciers melt down, you may have a trend analysis setting up within the data.
Okay. I just have one more question, or we'll do one more question. Do you have, and a couple people have asked questions about providing some links to some of the materials you reference, and just so you know, I will speak with the presenters afterwards, and we'll send out some of the references with the email tomorrow. The last question is, do you have an opinion concerning HiFran software? I guess, can you explain what HiFran software is? I believe it's an FFA software, but I don't know much beyond that.
To be honest, I'm not too knowledgeable on HiFran. There's other packages that I have seen out there. The one thing I would just caution people on is if you're using an American software, I would say, well, not at 1.9 times out of 10, they were limited to the log Pearson type 3 type distribution. So unless you have negatively skewed data, then you can, then yeah, go ahead and use it. But what I would be looking for in a software package is, I would probably be looking at a software package that doesn't just look at one frequency distribution, but looks at others. And I also would be looking for a package that also does a lot of the statistical tests that we had discussed earlier to determine whether or not the sample data qualifies for flood frequency analysis, such as tests for independence, randomness, stationarity, and homogeneity. So, and the other thing too is I probably would like a software that also does all the histogram plots too. So these are the kind of questions I'd be asking. So when you look at a software, in any software, always look to see what kind of features are built into the program. And as Chris was saying, one of the things he mentioned is also make sure the software is also compatible with your operating system too. Because as we know, that's one of the issues we've been running into CFA 3.1 now, which is the latest version, is right now it's not compatible with Windows 10. So you have to run a DOS simulator to be able to run it. I don't know, Chris, if you want to add anything.
Yeah, I think the HiFran program is probably a decent program. Um, I believe it's written by Bovee, so yeah, I think it's going to be half decent. And I've heard a couple of other consultants using that program too, just because of the frustration levels with using CFA. And I guess that was another reason, you know, back to having a Canadian product. Um, there was a lot of time and effort that went into CFA, and it's probably a very decent package, but the idea is trying to get it modernized, and getting things that users want in it is very difficult. And so that's why we kind of started this. If you have suggestions that you'd like to see in our program, then tell us, and we'll put it together and ship it out. At least get it in there or get it tried. I'd like to see more user input in the program rather than some agency creating it and users really don't get a chance.
Okay,
James?
well, thanks a lot, Chris and John.
Thank you.
Uh, Judging by how many questions we've got and couldn't actually get to, there's a lot of interest in this topic, and I guess putting it into practice across the Canadian hydrological context. So I think it's been very good. For anybody still listening in, again, if you wanted to contact John or Chris, their email is ewrg@idirect.com. And for any CSHS matters, our email is cshs@cwa.org, or you can go to greyjproject.org. Just a side note, you're probably getting emails about this webinar from Meg Olson. It's actually me who's, Meg Olson is the person whose name is on the webinar software. So if you see something from Meg, it's probably from me, though Meg's a great person and would be a delight to communicate with as well. So if there's any confusion around that, that's what's going on. And everybody who had signed up for this webinar will be getting a email with all this contact information and a link to the old webinar or to this webinar before that they can forward on to anybody. It should be accessible to the public for anyone to view at their convenience. So thanks a lot for everybody, and until next time, we do have a I don't know the date offhand, but there is a webinar on the R hydrology package coming up in January. So go to greyjproject.org if you're interested in that. And unless there's anything else to add, John or Chris, I think we'll sign off here.
Okay.
Thank you.
Thank you.
Thanks a lot. Bye.